Photoelectric effect and ultraviolet catastrophe within a unification framework. Structure, composition, and stability of positive electromagnetic orbits in atomic and stellar systems. Abstract. A unification framework is proposed based on structural and dynamical analogies between microcosmic and macrocosmic systems. Within this approach, atomic nuclei and stellar cores are treated as homologous entities generating coupled gravitational and magnetic fields. These fields give rise to stable orbital configurations interpreted as equilibrium loci within rotating field structures. The model offers an alternative qualitative interpretation of the photoelectric effect and the ultraviolet catastrophe, suggesting that both phenomena may arise from orbital saturation and particle redistribution processes. Although currently speculative, the framework provides testable predictions for both atomic and astrophysical systems. Introduction. The unification model presented here is grounded in the comparative analysis of structural and functional properties of systems across different cosmic scales. It posits that identical physical principles, structural organizations, and dynamical behaviors govern both the microcosm, atomic systems, and the macrocosm, stellar systems. This scale invariance motivates a unified interpretation of orbital dynamics and energy exchange processes. 2. Formation of orbital systems. Highly dense material nuclei, specifically atomic nuclei and stellar cores, generate both gravitational and magnetic fields. These fields are antagonistic in direction yet dynamically coupled. Gravitational forces act concentrically toward the nuclei, while magnetic effects originate in the nucleus and extend outward. Within this framework, the inward-directed gravitational interaction dominates nuclear cohesion, effectively replacing the conventional interpretation of the strong interaction as a distinct fundamental force. Conversely, magnetic fields dominate the orbital's regions, governing orbital structure. The interaction between these opposing fields produces a torsional effect, resulting in system-wide rotation, spin. This rotational behavior is intrinsic to all systems composed of a central nucleus and surrounding fields. 3. Electromagnetic orbits as equilibrium structures. Due to rotational dynamics, the inner regions of the field structure rotate faster than the outer regions, generating a spiral configuration. Radial intersections within this spiral define loci of dynamic equilibrium, where the spatial configuration remains invariant relative to a non-rotating nucleus. These loci correspond to stable electromagnetic orbits. Thus, positive electromagnetic orbits are defined as radial distances at which structural and dynamical equilibrium is preserved independently of rotational state. They may be interpreted as equilibrium, rest points, within a rotating and deforming field system. 4. Orbital occupation and stability. A key assumption of the model is that all potential orbits tend toward occupation by material entities. This occupation is necessary to define system orbital coordinates, mass distribution, and energy density, ensuring compatibility with the average energy density of the cosmos. The occupying entities are typically discrete bodies, electrons in atoms, planets in stellar systems, with characteristic sizes approximately 10⁻³ to 4 times smaller than the central nucleus. This scale separation allows the magnetic field of the orbiting body to remain confined within the orbital structure. In certain cases, orbits may be occupied by multiple smaller particles whose combined mass is equivalent to a single electron, or planet. Examples include asteroid belts and systems analogous to so-called free neutrons. Over time, such distributed matter tends to aggregate into a single stable entity through collisional processes. The timescale of this transition depends strongly on the cosmic scale, minutes in atomic systems and up to 10⁹ years or more in astrophysical contexts. V. Photoelectric effect and ultraviolet catastrophe. Within this framework, the photoelectric effect is interpreted as a consequence of intense orbital saturation by high-energy photons that reject the electron outside of the orbit. When sufficient ultraviolet radiation is supplied, outer electrons may be displaced or ejected, or transition exterior orbits, all that consistent with bow-type descriptions. Similarly, the ultraviolet catastrophe can be qualitatively explained as a redistribution process. Under intense high-frequency excitation, e.g., blackbody radiation conditions, electrons may absorb energy to transition to higher orbits rather than re-emitting it. This leads to a suppression of expected emission at high frequencies. 6. Astrophysical extension and predictions. The model further postulates that analogous processes may occur in stellar systems, where high-energy impacts could induce orbital restructuring or particle redistribution. At present, these extensions remain theoretical and lack direct observational confirmation. However, the framework suggests several avenues for future investigation, particularly in the study of energy transfer mechanisms across scales and the stability of orbital configurations under extreme conditions. 7. Conclusion. The unification model provides a qualitative, scale-invariant framework for interpreting orbital structures and energy exchange phenomena. While speculative, it offers an alternative perspective on established effects such as the photoelectric effect and the ultraviolet catastrophe. Further theoretical refinement and experimental validation are required to assess its physical viability.